think I've ever felt so warm. All my roots sprouted into split ends. The smell of linen stains my arms. I think I finally understand it now. Oh, life's much too long to not fall in love, but much too short to keep waiting around. We run ourselves into the ground. young to not fall in love, but much too short to keep waiting around. We run ourselves into the ground. Tell you, ooh, but deep down I think you already know if patience is a virtue.
Hi! Hello, Orbeez! Sorry, I had to pause the music. I was really jamming out, though. We're gonna switch to the main screen. Give me 1 second. Hello! Hi! Speeding at Seeds, Meezy! Good morning, everybody! Hi! I'm actually on time today, which is very, very good. If you guys may notice, my voice is a little bit out. I was actually sick this past week and I just finally recovered. It was probably the fastest illness that has ever happened. It was like day 1, I like woke up with a sore throat, and then day 2, I woke up with like an even worse sore throat. And then like day 3 and 4, I didn't have a sore throat, but I had like a bit of congestion in my nose, which is still a little bit around. And then day 5, I was coughing a little. And then now I'm like back to normal. So I like kind of speed ran the illness, but I have a warm glass of English breakfast tea here, and I am definitely going to stay hydrated. She even speeds through colds. No, that is not true. I typically take a really long time to recover. When I was younger, I had pneumonia for like 2 months, so this is a very special occurrence. I hope the music isn't too loud, but I'm going to quickly go ahead and do attendance. So if you are here, please say here. Hello, Pembu, good morning. Hello, Matt. Hello, Zilla. Hello, Astral. Hello, Caffeefile. Glad you're finally able to join. Hello, Eggy. Hello, Matt. I hope you're staying safe from the storm. I heard the big one that's kind of stretching from Lake Erie all the way down to Texas is in the process of hitting, or is hitting right now. Hello, Liam. Hello, Yao. That's a very interesting nickname. Hello, Andrew. And then on the Twitch side, hello, Kami. Hello, Lankuri. Hello, Endless Dessert. Hello, Hi Wyon, first time chatter. I caught a flu or cold yesterday. Feels quite mild so far. That's good to hear, yeah. I feel like there's definitely been some illnesses going on with the colder season. The man flu? What's the man flu? It's hitting Texas all right. It's cold, just not too cold yet. I've been seeing videos of like trees exploding because when trees suddenly cool, like the sap in the water expand. A little bit of physics there. And the trees literally explode. So that was really freaky. And then I saw another video of somebody in like Chicago having like a water bottle and then bringing the water bottle outside and it like freezing over. That was also very crazy to see. In terms of announcements, 2 Z streams, 1 weekend. What? Yes, so tomorrow I am collabing with Stella, who is a new VTuber in the astronomy VTuber space. And we are going to be showcasing our favorite books, which ended up kind of being like a nerdy book showcase. It was so much fun prepping for this stream because we were DMing each other and being like, hey, like, have you read this? Have you read this? And we had like slideshow, like a Google slideshow that we were preparing for this stream tomorrow. And I'd be like going through the slideshow and like realize that Stella put a book that I like didn't put down. And so I like comment on the slide like, oh my god, this book is so amazing. And we were just nerding out in the process of making this collab. So I'm really excited to share it with you all tomorrow. Always keep warm, fellas. Cold here in PH, especially at night. The wind chill was negative 25F. That's crazy. That is crazy. Yes, definitely stay warm. Definitely stay safe. I don't know how badly the storm is hitting in certain places, but I did hear that, like, in some places, like, the grocery stores were being overrun with people, like, mass buying groceries and that kind of stuff, too. So definitely stay safe. Oh, wait. Google's telling me to log in. Give me 1 second. Okay, great. Alright, so I'm gonna make this a little smaller. So I hope to see you all tomorrow as well. It'll be at 10:30 a.m. PST, so that's about an hour and a half from what time it is right now. So hopefully the morning folk can also catch it too. Yeah, this tea is really great. It's just a plain English breakfast tea, but I like mixing it with oat milk. Oh my god, everything I have on my desk is falling. Yeah, so, I guess before we start reading articles, I did want to briefly mention, like, what my schedule looks like, just because I'm very excited to share this. So next week, I'm probably going to be streaming again on Friday, and then there is a collab that's happening on Saturday, with a few familiar folks. I think this is probably one of the biggest collabs that I've been part of, excluding the LA Wildfire Relief fundraiser that I did. So it's gonna be a great time. Stella the chat cat is perfect. Yes, Stella is absolutely amazing. Alright. What cat? Oh yeah, I'm collabing with Stella tomorrow, and she is canonically a cat VTuber. Alright, let me get the article loaded up. I am really excited to share this first article with you guys. I have pinned it in the Twitch chat and in the YouTube chat, I've confirmed. So this is the article that sort of got me thinking about doing this stream, and probably the reason why you clicked on it in the first place, because let me just show you. I like, if you look at this image here, doesn't that look a little suspicious? A little suspicious? Well, we're gonna be reading this article, so yeah. We actually have a few articles to go through. We have 3 articles, and then one fun one that we'll get to if we have time, that is not related to exoplanets, but is apparently called like the Z Machine or something, so I thought it would be cool to read. Hello Cranberry Crook, thank you so much for joining. What are you canonically? I am canonically a photon from the cosmic microwave background. I am the first light of the universe itself. Yeah, so without much further ado, I think we should just get on to reading. And of course, I always have this disclaimer beforehand. Feel free to ask me questions. That being said, I am like vaguely familiar with exoplanets, but I will try my best to answer any questions. But this is also a learning space, so we can Google stuff together and figure things out. In addition, for those of you who do not know, the articles that we are reading from are from this website known as Astrobites. They are an amazing source if you want to get into reading astrophysics articles on the regular, but think that like the actual research articles might be too overwhelming or too technical. What Astrobites does is that they take research papers and they sort of translate them into lay-friendly terms. What that means is that they make the articles accessible for anybody to read without a background in exoplanet research or a very specific field of astrophysics. And when I was first starting out, this was definitely a great way to just read articles from many different fields of astrophysics. And they also have bites for different fields. They have like one for particle physics, math, like I think one for like marine biology. So really, really great source. Highly recommend. I can't wait to hear all the long words I've never heard before. Well, there probably are a little bit of long words. I mean, the title of this also seems to have some long words, but these articles do a really good job of breaking things down. So yeah, and if there's a word we don't know, we can also search it up together. So I'm very, very excited. Z, you can't be spreading Among Us propaganda. I love Among Us. I love Among Us. The moment I saw this article, I was like, I have to do a stream on it. So, yes. So let's get started. So this article is named, Forming Giant Planets, Your Stellar Neighbor's UV Light Could Be a Problem. I love these titles always, they're so creative. And the original research paper, which is linked here, is a far UV-driven photoevaporation flow observed in protoplanetary disk. And this is a guest post written by Matthäus Bernini-Perrin, a final year PhD student at Heidelberg University in Germany. Since completing his bachelor's degree in astronomy in Rio de Janeiro, Brazil, his research focused on massive stars. During his master's, he began studying the winds and has been doing so ever since. Outside of astrophysics, he enjoys swimming, dancing, and drawing. Well, hello, Matthäus. Thank you for writing this article. So let's get started. Oh, okay. A stellar system, like our own solar system, forms when the gas and dust disk that orbits the central star, also known as a protoplanetary disk, collapses into planets, moons, comets, and asteroids. However, in star-forming regions, low-mass stars also coexist with big, hot, freshly formed massive stars, which emit a lot of radiation and wind. For the poor, low-mass stars trying to sculpt their own planetary system, this is not good news, because the radiation and wind from the massive stars disrupt the planetary system, it seems. In today's article, the authors discuss how massive stars in the trapezium cluster affect planet formation around a young low-mass star, D203506, yes, an ugly name. I wonder what this, oh, okay, in the Orion bar, which is part of the Orion Nebula. They show that the incoming radiation from the massive stars is sabotaging. Wait, there's no way that this dude included that word without the intention of referring to Among Us. The formation of giant planets. Crazy, right? Then let's now dive into how the authors found this out. If there's another Among Us reference in here, I'm very sure that Matthäus put that on purpose. Is this how the moon formed? Well, I think we're talking about protoplanetary disks. So that kind of discusses how the planets formed. The moon formed when a planetesimal or like a large body hit the Earth, and its debris like formed a ring around Earth, which then coalesced to form the moon. But protoplanetary disks are huge. They're the stuff that goes around stars. So these are basically the formation of the planets. Molecules are the clues. Essentially, the aim of the authors was to analyze how the dust cocoon, or protoplanetary disk around D203506, is interacting with the UV or ultraviolet radiation of nearby hot, massive stars. In the zoomed-in region of the right panel of Figure 1, you can see the dust cocoon as a dark red blob. Okay, there's no way that does not look like Among Us, which is the ionized gas of the western edge of the Orion bar. Okay, so let's read the figure caption, then I'll zoom in. Optical and near-infrared images of the Orion bar region. So the left panel here is the Hubble Space Telescope image. Wait, let me see if I can zoom in a little further. Oh, I guess not. Okay. Here. Hubble Space Telescope optical image. On the right panel is the James Webb Space Telescope near-infrared image of the same region at the same scale. I think another really good comparison between these two is you could just see the amount of detail. For the Hubble image, like there's great detail, but for here you can really see the clouds and the filaments pop out. Naturally, the colors in this image are false colors to represent the amount of radiation in a specific frequency band. The white dotted line highlights the ionization edge of the Orion bar caused by, okay, so this white dotted line here, by the incoming UV radiation. The protoplanetary disk of D203506 is the dark red blob, so this, with a distinctive blue glow, caused by a jet of material emitted from one of the star's poles that is shown in the zoomed-in image of the right panel. Well, okay, I'm gonna try to open this image in a new tab and zoom in. There we go. Okay, wait, hold up. Oh. Okay, that's a little bit better. Yeah, I mean, so this is the protoplanetary disk, and the light from it is apparently coming out of a jet from the stars. Okay, there's like no way that like does not look like doesn't that just look like an Among Us in space? Researchers, scientists do be naming majestic heavenly bodies with D5642 and just call it a day. That is true. But astrophysicists are really great at naming things, like the Very Large Array, the Extremely Large Telescope, or I went over an article once that was literally titled Hot Diggity Dog in reference to these like hot dog black holes. So we love naming things. Where Z lives, yes, I actually am from here. The TMT telescope, yes, the 30-meter telescope. Yeah, no, this literally looks like an Among Us. This is beautiful. Can't something be named Bob? I mean, I'm sure it could be. I'm sure that there's something named Bob out there. All right. So let's keep reading. The Among Us emojis in chat. The UV radiation from nearby stars has the ability to break molecules, disassociating their atoms. Therefore, by looking closely at regions where molecular gas is destroyed by such UV photons, called photodissociation regions or PDRs, it is possible to quantify how the planet-forming process is impacted by those nearby hot stars. The PDRs can be identified and mapped by looking at spectral signatures in the infrared regime of molecules such as hydrogen gas, oxygen gas, organic molecules, and other molecules. Oh yeah, so this actually got me thinking. I am preparing a presentation on spectral energy distribution fitting, which is a strategy that a lot of galaxy astrophysicists use in order to decipher the light from these galaxies. So I think this is also a great example of this. So how can we look at an object and just gather its light and figure out all of its properties? For instance, for a galaxy, how can we take an image of it and know its mass or how it's evolved over time? Those are really difficult things to decipher. Well, a lot of it has to do with spectra or spectral energy distribution fitting, which is what we do when we gather only specific parts of the object's wavelength. And from that, we can piece together a lot of clues about the object. And so I think here they're doing something similar where they're getting these spectral signatures of these different molecules to try to understand how these molecular gas regions are being destroyed and how that affects the process of forming planets. How long until Z names something? What's there to say that I already haven't named something? Decipher, like as in analyze and stuff? Yeah, I like to use the word decipher because it's kind of like being like a light detective. You basically have very limited clues of an object's light, and from there you need to sort of be a detective and use those clues to figure out all the properties of the object that you're looking at. You discover you can call it whatever you want within reason. Well, that being said, the very numerical systems are... Whoa, my eyes were really weird for a second. The numerical system is there so that it is easier to classify and quantify different objects. Now, if everything had a name, it would be very difficult to keep track of things, especially when we're at a point where we're discovering millions of objects. For instance, with the Rubin Observatory, I gave a presentation on this a while back. We are going to be getting like 1.2 million notifications every night. So that's like 1.2 million things being detected. That includes asteroids, supernovae, like star explosions. And there's no way that somebody, I mean, I probably could, honestly, but you know, there's no way that one person could sit down and name all of these millions of objects. And so a numerical system is very useful for that. Whoa. Sorry, and for those of you who came in, I am recovering from an illness, so I do sound a little bit congested today, but we will figure it out as we go. I'm sipping on tea. All right, so let's keep on reading. Okay, so let's learn about these photodissociation regions. In figure 2, we can see images of the D203-506 system at different wavelengths and the observed infrared spectrum crowded with molecular and atomic signatures. Okay, let's see. So these are very different images. Okay, like this literally looks like an Among Us. Okay, so let's read. Upper square panels A through I, so this 3x3 grid. Images of D23506 at different frequencies, optical, infrared, and radio obtained using the Hubble Space Telescope, so this one. The James Webb Space Telescope, which are B through F. Like, I'm really impressed by the difference in resolution. I know that's not the point of this figure here, but it really stands out. And ALMA, which is a radio telescope, which is panels G through I. So those are the ones here. Each wavelength range reveals different structural features of the disk. Yeah, so I guess this Hubble one just looks at the visible dust. And then the James Webb one are looking at infrared. So you can kind of see the Among Us structure kind of pop out. And the radio kind of just looks like an orb, except this one, which is a higher frequency. And then the bottom panel is the infrared spectrum of D23506 obtained with the James Webb Space Telescope. So they really got all of the intensity over the wavelength spectrum. So that's what a spectra is. Signatures from different molecules and dust are present and identified. I see. So they have HI labeled here, or H1, and then H2, OH, CH plus, and CO. So they have hydrogen, iron, H2, HCN, organic molecules. Great. Cataloging things with just a serial number is exhausting. Imagine trying to give them proper names like Steve. Oh, does the light from being reflected by the object being observed subject to change when it passes through mediums? Say, air in the atmosphere. Wouldn't that affect the accuracy of deciphering? Oh, so you mean like when the light... So when the light goes from the object and it travels through space to Earth, would it be affected by the atmosphere? Well, the spectra here is gathered by the James Webb Space Telescope, which is a space telescope. The only telescope here that's listed as on the ground is ALMA, and that is a radio telescope. There's a really great diagram of how different light regions penetrate through the atmosphere. Let me see if I can quickly pull it up. There's this really famous diagram. And so there's a reason why we can build radio telescopes on the ground. Oh, I pulled it up, but it was like really blurry. So let me try to get a better one. This is not the one I'm looking for. Okay, I think this might suffice. Okay. Let me pull this up. This might be a helpful visualization. So what this shows is wavelength on the x-axis and atmospheric opacity. And so for certain wavelengths, we simply cannot see them from the ground, such as gamma rays, x-rays, and ultraviolet light, which are blocked by the upper atmosphere. That's honestly a good thing because, I mean, these are very, like, highly energetic particles. So visible light is observable from Earth with some atmospheric distortion. But when we're dealing with the infrared spectrum, which is what we're looking at here, which is very helpful for us because we're looking at this hot dust, which is in infrared. It is absorbed by atmospheric gases and is best observed from space. And that includes things like the James Webb Space Telescope. Now, the last telescope that I mentioned, ALMA, which was the bottom row of that panel, is a radio telescope. And it's based on the ground because radio waves are observable from Earth. And you can kind of see it here, where this spectrum kind of opens up. And then anything longer than that are blocked. So this kind of shows why we have certain telescopes at certain frequencies on the ground or in space. So I hope that helps. And then to go back to the slide. All right, so let's keep on reading. Each wavelength reveals different features, which are produced by different molecules and physical processes, allowing us to understand the structure of the system and the different phenomena that are happening in it. Yes. Namely, a bright emission spot can be seen in multiple frequency bands, which indicates excitation by UV radiation. This brighter region seemingly coincides with the interaction region with the trapezium cluster radiation. From the physical interpretation of these images, the authors developed the schematic representation of the system that is shown in Figure 3. Oh, I love this figure. I love when papers make these really great visual figures. That includes things like these. There are also some figures where they show you the entire like pipeline or sort of the process behind how they got from one data set to another. I absolutely love when authors do this. I know quite a few people who use Inkscape, which has a very steep learning curve, in order to create these gorgeous figures. So kudos to the authors. I love this diagram. We're gonna dissect it in just a moment. Hello, Gur. Lucky I found this channel. Well, I'm very lucky that you're here, so thank you so much. What are we doing today, Z? Hello, Silo. We are reading about how exoplanets form, and we're starting with an article about these protoplanetary disks, or sort of precursors to the solar system that look like emoji. So yes. Wow, a lot of people came in. Hello, Parafergon. Hello, Stella. Hello, Red. Stella, you may be very happy to see that I was pitching our little collab tomorrow. I'm so stoked. And for those of you who haven't already, go check out Stella's channel. Let me just copy and paste the link real quick. Boop, boop, boop. And then for the Twitch folk as well. Boop. Inkscape mentioned, yeah. I've only used Inkscape for laser cutting, actually, but I heard it's very good for building figures. I also use this website known as BioRender, which is supposed to be for biology figures, but it's very gorgeous. It's very aesthetic, especially if you need really good diagrams quickly. And if you are in biology too. Let me pull up their little... Yeah, it's mostly for biology folks, but like, look at how clean this looks. Look at that! Look at that! I don't do anything related to biology, but I am a simp for good figures. So yeah, no, it's great. Oh, they even have like templates and stuff. Like here, I'll just... If BioRender sponsors me, that would be the dream. I don't know if they have like a product, but I would be happy to do a sponsorship with BioRender. Like, just look at how aesthetic these are. I think that visuals are so useful to help understand concepts. I mean, like something like this too, and just like the contrast is just so immaculate. Anyways, sorry. very unrelated to exoplanets here, but I used Inkscape to make flags of fictional countries. Whoa, interesting. Yeah, no, it's great because you can download your files as very diverse types and very high quality files, such that you can just paste them into Overleaf or wherever you build your research papers. If I recall correctly, another advantage is that you can save the figures such that you can also select text, which is a great advantage too. I've used Inkscape to chop up PDFs, yeah. All right, so let's take a look at this schematic. Schematic interpretation of the system based on the analysis of infrared and radio wavelengths. Oh, hello. I cannot read from that small font. Hello, Adult Things. Thank you so much for subscribing. Schematic interpretation of the system based on the analysis of infrared and radio wavelengths shown in Figure 2. Each component highlights features produced by different molecules. Oh, thank you. Wow, that's a very interesting username. Thank you, Aggressive Fart, for following. Each component highlights features produced by different molecules. In this diagram, the dark brown slab represents the protoplanetary disk, consisting of cold molecular gas seen edge on. The small brown arrows popping out from the cold disk show the gas. Okay, so these small arrows show the gas escaping via photoevaporation, which feeds the envelope, which is this light brown blob. Okay. At the outer boundary of the envelope. Oh, thank you, Akrunu, for. Oh, thank you, Akrunu, for following. At the outer boundary of the envelope. What's going on? Thank you, High Potential, for following. Wait, was there a raid? Was there an unofficial raid? Catapulting in space at V-Escape, it's Stella VT. I'm not sure if there was an unofficial raid, but, well, thank you, Stella, potentially? Or maybe this was just a pure coincidence. Sorry, I keep getting interrupted. Let's actually read this figure. But thank you for the support. The photo dissociation region is precisely the transition. Raiders? No. The photo dissociation region is precisely the transition from the innermost to the outermost parts of the envelope. The light blue lines represent the jet of ionized iron emission lines observed in the infrared, which is emitted from the poles of the centered star. In the region where the jet interacts with the PDR, one sees a bright spot in the infrared regime. Okay, let's see. It wasn't me. Oh, okay, well, thank you for all the sudden support then. Figured I'd follow on here if I'm ever there, but on my internet, it's easier to watch on YouTube. I just came independently. Oh, well, thank you, Akrunu. Thank you so much for your support. So let's take a look at this image. So there's a star at the center here that is creating this jet, which is what we're seeing here, this bright blue region. And there is this edge on disk. So this brownish part is the protoplanetary disk, like a precursor to a solar system. And these pink arrows represent this ultraviolet radiation, which is coming from the trapezium, which is this bright star cluster in the Orion Nebula. And so what they're claiming is that this region here is the photodissociation region, where the UV radiation is kind of blowing things apart. Very interesting. Wow, this is a very interesting diagram. I found this channel a few weeks ago when you had a collab with for his Donathon, and also we worked on a video together. Catching the sabotage. There is no way. Mateus is, there's no way that this wasn't intentional. But we shall see. I just want to say I've been following you on YouTube for a while. You have to be my favorite VTuber. Hope you'll continue to make content and get more popular. Thank you, Lil Dragon Uwu. That really means a lot. I'm really glad you're enjoying the content. I'm sorry I can't stream as often as some of like the bigger VTubers, but you know, doing content like this genuinely is super exciting to share with you guys. All right. Let's continue. The authors used sophisticated radiative transfer and molecular physics models to produce synthetic or artificial spectra. By comparing these, so they kind of simulated the light, with the observed spectrum of D203-506 and photometry multiple wave bands, the authors inferred the density and temperature of the blob's gas, which is about 1,000 degrees Celsius. If one knows about the density and temperature, it is possible to infer the speed of sound, the speed from which sound or vibration propagates through a substance. By comparing this with the orbital speed, the velocity at which a particle should follow a stable orbit around the central star at a certain radius, the authors could derive the maximum radius at which the particle could be gravitationally bound to the central star. This is called the gravitational radius. The authors determined a gravitational radius of about 26 AU. So an AU is the distance from the sun to the Earth. And this is smaller than the size of the region that emits H2 transition, about 130 AU. This indicates that this gas is largely unbound to the star, and therefore is flowing away from it. From the speed of sound, it is also possible to calculate the mass outflow from the system and the mass loss rate, how much mass is lost per unit time, which is about 0.1 to 4.6 solar masses per million years. I wonder why this range is so big. I wonder how they got that. Maybe there's more details in the paper. These values of mass loss rates are consistent with those obtained by means of a more detailed radiative transfer and hydrodynamical model, which the authors computed as a sanity check via an independent method. Okay, interesting. So basically they simulated the light from this object, and by comparing their simulated light to the actual light that they saw, they were able to piece together how quickly the object is losing mass. So, implications for planet formation. Gas in protoplanetary disks is a basic ingredient for forming gas giant planets, such as Jupiter and Saturn. Therefore, if a disk loses its mass due to the incoming UV radiation destroying the molecules and pushing the gas away, the formation and growth of these big planets can be suppressed. So that's one of the reasons why they're studying this object, because they're thinking that the radiation from this bright star cluster would be pushing the gas away such that planets couldn't form. How much a stellar system in formation can resist the UV radiation from hot massive stars in its vicinity will depend, of course, on the strength of this incoming UV radiation and on the mass of the central star of the system. The authors discussed that if the UV radiation hitting the disk is 500 times higher than the radiation in the solar neighborhood, the formation of giant planets around stars 50% lighter than our sun, which is the case for the majority of stars, is suppressed. In D23506 Misfortune, its mass is 1/3 of the sun's mass, and the incoming UV radiation is 100,000 times the radiation of the solar neighborhood. Well, the Trapezium star cluster is an incredibly bright star cluster. This implies that the disk should dissipate faster than giant planets can start forming. RIP, so no planets in the Among Us protoplanetary disk. This might be the reason behind the correlation between the host stellar mass and the presence or absence of more massive exoplanets. Namely, in a star cluster, while the young stars are making or trying to make gas giant planets, the UV radiation from the neighboring hot massive stars severely suppresses planet formation. Essentially, if you are a star but not massive enough to protect your disk, you may need to give up the idea of having a Jupiter-like planet entirely. This is so tragic. This is so tragic. In fact, according to the authors, our sun's apparent lack of bigger planets might be the result of massive stars sabotaging its disk with their UV radiation. Oh, that is interesting, but I thought... Whoa. The solar system does have quite a few giant planets, or does it mean planets larger than Jupiter? It's as hot as a microwaved hot pocket. A singular microwave hot pocket's going to stop the formation of gaseous planets. Gotta sleep now. Thank you, A Yao Yao Yao, for joining. Ooh. I needed to drink some tea. Yeah, I think from the context, it's just like super Jupiters. Yeah, I think that's what it's referring to as well. Wow, this was really interesting. I did not know about a lot of this. Makes sense that the region interacting with the jet heats and emits in the infrared, but what mechanism specifically could cause the bright spot in the PDR uniquely? Or is it just that other regions in the jet... Oh, so you mean like what's causing this bright spot? I think the jet is sort of heating up the material so that it creates a bright spot. It appears that this photo dissociation region is not necessarily the area that is bright. Or is it that other regions in the jet path are being filtered through the envelope? Yeah, I hope this answers your question, but it seems like the jet and the bright spot are correlated, and it doesn't really have much to do with the PDR. That being said, I'm gonna try to open the archive link. If you click the link, you can also go to the archive link. Oh, this is quite a short article. Here, let me show this. If you go to the top of the article, you could read the original article. and take a look. Though I think the bright spot isn't related with the photo dissociation region, if I recall correctly. Get well soon. Well, I'm recovering very quickly. I've actually been getting quite a bit of sleep in order to recover. And I feel like the best way to get over an illness is to just sleep it off. I've also been taking like medication for like congestion, stuff like that. But my voice is still in not ideal state. We'll check it out. Yeah. Yeah, I'm not quite sure. So let me load up our next article in the meantime. Planetary hit and run. Oop, that didn't work. I think honestly, as many of you guys may know, I was traveling recently. And so I think when I got back, there was a lot of stuff to catch up on. And so as a result, I felt like when I came back, I definitely felt very fatigued, which was why I think I got the illness. Plus, you know, being in a space with a lot of people, there's a lot of illnesses and stuff going around already. I think after almost like maybe like most conferences I've been to, I always get like a little bit sick, whether that's just from like walking around a lot or talking a lot or like actually getting like a cold or something. But this has been really mild, so I'm not too worried. The worst situation I was in was when I came back from a conference and I had like some sort of like stomach virus. And that was very, very unpleasant. Yeah, so this next article has a very fun title, A Planetary Hit and Run. Sounds like con flu. I think it's just a consequence of just a lot of people being in one place at once. Plus, I guess, like, another thing was, I remember for some of these conferences, you know, things are so busy, like, I wouldn't have a lot of time to eat, or, like, you know, I'd be drinking a lot of coffee, and so I'd be missing out on, like, vegetables, or, like, fruits, all those things that, like, boost your immune system. But I recently started taking, vitamin C supplements, which have been very, very helpful, or, like, things like Airborne. It's like this tea, it's like this fizzy tablet which has like a bunch of vitamins in it. Yeah, and when I'm sick, I like try to take these like gummy vitamins, and I think you're supposed to take like 2 usually, but I usually only take 1, and then when I'm sick I take 2, and that really helps me recover faster. Yeah, your vitamin C intake, yeah. I make sure not to take too much because I heard there's some consequences for that. Stares at Z like a mad dad. No, I've been helpful. I've been healthy. I've been healthy. This cold or whatever I have has been really, really mild. I think it's also worse in the morning and the evening, but during the day it's been fine. Yesterday I actually was feeling quite good. I went out to get a matcha with a friend, which was a lot of fun. And I felt like after that I was in pretty good condition. I heard matcha also has some like antioxidants or something, so I don't know if it helped, but maybe. Or maybe I just say that in order to defend my my healthy consumption of matcha. Too much vitamin C, you just pee it back out. Yeah, I think that's exactly what happens. Too little vitamin C, and I think you get scurvy or something. Alright, well, I'm ready to read the next article. Gummy vitamins, every time I get my hands on, I end up eating them like candies, which is not a good idea. Well, there are far worse things that you could be eating like candies, so I don't think gummy vitamins are the worst. But that being said, please make sure to check the correct dose and everything. So this article is titled The Possibility of a Giant Impact on Venus. Very interesting. Venus is very cool. I actually recently did a poll in the Orbeez Discord about what people's favorite planet were. Wow, that sentence had zero grammatical structure. What everybody's favorite planet is. And Venus actually got a lot of votes. And I am really interested in Venus because we haven't been back there in a really long time. It's a very active system. It's regarded as Earth's twin, but it's very, 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 very different from us. I think this article is going to start out with this. And one of the things that I'm personally very curious about is, like, how did it get to that point? And by now we've kind of pieced it together. It's very geologically active. There's literally like lava flows and everything. But it's very fascinating to see how a planet that can be so similar can end up on such a different pathway from Earth. Oh, thank you, Pembu, for the Discord link. Venus is insanely interesting. I agree. Too much vitamin A is a thing. I heard that eating too many almonds is also a thing, because you could get kidney stones. And so whenever I have almonds, I only have like 7 at a time. Hello, Tylenol. Thank you so much for stopping by. All right, so let's read. Earth's twin before we screw it up. Yeah. Venus is commonly regarded as Earth's twin due to its similar size, mass, rocky composition, and location in the inner solar system. These similarities might lead you to expect a familiar atmosphere and landscape. Instead, where Earth harbors lush forests and shimmering blue oceans, Venus offers only scorched plains, volcanoes, and sulfuric skies. Further, unlike Earth, Venus has a retrograde rotation at a very slow speed and has no moon. These stark differences call into question how Venus diverged so dramatically from its twin. The authors of today's paper propose an answer as violent as the planet itself, a car crash of planetary proportions. Wow, whoever wrote this article is cooking. Setting the scene of the crime. Today's such an Among Us themed stream, Orbeez. Since we cannot travel back 4.5 billion years to witness the solar system's formation, we must work backwards from present conditions to reconstruct the past. Simulations of the early solar system reveal that giant collisions were very common, making Venus a likely target during its youth. But what kind of collision could explain Venus's peculiar state? Giant impacts can dramatically alter a planet's angular momentum and form moons. Yet Venus rotates unusually slowly and has no moon at all. The authors investigated whether a giant impact could be consistent with both of these observations, and if so, what initial conditions would be required. To test different scenarios, the authors employed a suite of 3D impact simulations using the smooth particle hydrodynamics method. I'm sure this links to their... Oh, okay. It links to a Wikipedia article. A commonly used computational method for simulating the mechanics of solid body interactions. With these models, they vary the parameters that would set the initial conditions of Venus and the impactor before the collision. Those parameters are the impactor mass, the impact velocity, the impact parameter, oh, so it's like the angle, and the pre-impact thermal profile of Venus. They also include models where Venus has an initial rotation speed, and others where Venus starts with no rotation. They run a total of 81 simulations with varying initial conditions and categorize the outcomes into scenarios. Merger, graze and merge. Graze and merge, that's such a cool name. And hit and run. Wait, that's actually what it's called. See, astronomers are great at naming things. In a merger, at least 95% of the colliding mass remains gravitationally bound to Venus, essentially creating a single combined body. A graze and merge represents a 2-stage process where the impactor grazes Venus during an initial encounter, enters a temporary orbit, and then collides again, merging permanently. Finally, in a hit and run, the impactor skims Venus, but escapes its gravitational grip entirely, leaving 2 separate intact bodies that drift apart after the collision. The authors then compare these post-impact Venus models to its present-day properties to see which ones could have led to the Venus we observe today. This is so cool, what? Also, the names for these are amazing. When creative writing meets academia. See, this is what I love about these articles. Because they not only translate concepts into terms that are, you know, a lot easier to digest, and they have the resources where you can learn more about specific scientific terms, but, you know, they're just also having fun, and that is what astrophysics is at the end of the day. It's fun, it's cool, it's really amazing. Yeah, it also spins about its pole retrograde, so there's got to be some weird history behind that. Yeah. I eat too many almonds and Nep yells at me. Yeah, no, Nep and I did a brief collab where she explained why purchasing almonds in California is a horrible thing to do. It has to do with like their water consumption and that they like import bees. It's very unsustainable. You should definitely ask her for more details. I'm not doing the explanation justice, but yeah. Yeah, no, this is great though. Wow, these simulations look incredible. I'm very surprised that they look very hydrodynamic. So what I mean by that is for something like this looks incredibly symmetric. I'm curious about what initial conditions they put in for the structures of these bodies, but maybe they have a bit of description here. Oh, thank you, Magical Plesiosaur, for following. I also realized that I have 2 alerts. I'm gonna get rid of this one. Whoa! Oh, we reached our followers goal of 300 on Twitch. Thank you so much. I actually didn't even realize that I set that goal, but yippee! Yeah, I just recently started dual streaming on Twitch, so thank you so much. Thank you, Magical Plesiosaur, for being the 300th person. Astrophysics, hell yeah. Yeah, that's exactly the right reaction. All right. So we are going through the simulation, so let's read about what's going on here. Snapshots of a cross-sectional slice of a head-on collision between a non-rotating Venus and a 0.1 Earth mass impactor 10 kilometers per second. So that is this half here. A head-on collision. I mean, this literally looks like a head-on. So this must be the 0.1 mass collider. This looks quite large in radius. I wonder what assumptions they made for the density of this object. And so this object is literally just colliding straight into here, and it creates this. Is this in hours? That's really... Oh, so it goes 0 hours, 0.2 hours, and it kind of progresses. And then after 80 hours, it looks like everything has kind of settled down. That's actually very surprising. I'm sure they have more details about what exactly they were simulating here in the paper, though I'm very surprised that everything is getting differentiated. So what I mean by differentiating is when planets form, or I guess in this case when a collision happens and material kind of has to come back in, the less dense materials kind of go to the top and the more dense materials go to the bottom. So if you kind of think of it like if you pour like oil and water and a bunch of things with different densities like you did in your high school lab or something, you notice that the materials separate out naturally over time. And that process takes time. And it actually happens inside planets as well. So that's why the Earth has layers. That's why the planets have layers. And the reason why I'm saying that I'm surprised is because it seems like this differentiation, this kind of like onion structure, is already happening 80 hours in. And so I guess, I mean, this looks very symmetrical as well. It looks very hydrodynamic, very fluid-like. Very interesting stuff. I'm more into paleontology, but astrophysics is so interesting too. And maybe... Oh, thank you, Kyle, for following. And maybe Venus and Mars had life around 2.3 billion years ago. Yeah, I am fascinated by the idea of Mars potentially having life a long time ago. I mean, it has structures that are reminiscent of rivers. This would destroy all life on Venus. I mean, I don't think this would be very pleasant. I don't think, you know, somebody would survive this impact. Well, let's see what's going on here in the second half. Snapshots of a cross-sectional slice of an oblique collision between a rotating Venus. So before it wasn't rotating. I guess that's also why it looks so symmetric. And a 0.1 Earth mass impactor, so this thing, at 10 kilometers per second. This collision is classified as a hit and run. Yeah, differentiation 80 hours after impact. Yeah, I think they're making a lot of assumptions here. But we'll read more about exactly what they were hoping to extract from the simulation. Oh, so this is the hit and run. You can kind of see the object kind of sliding past and doesn't actually amalgamate into this, which is Venus. Wow, there's a really long tail of material that emerges out there. And then it kind of does that. And you can kind of see that Venus is rotating. And it kind of looks the same at the end. I wonder if they have like animations of this. This is super cool. Finding the suspects. Orbeez. Okay, wait. I have to be so real. I just chose this article because it had a cool title. I didn't realize that it would be Among Us themed yet again. Hello, Kyle. Thank you for the first time chat. Is the blue the atmosphere of the whole planet and the dark part is the core? No, I think this is representing the different layers, like the geological layers of the planet. Does the material in the tail just fly off in the sun? I'm not quite sure, I guess? Or there's such a big time jump between these two panels. I'm wondering if the material just kind of comes back in and starts rotating around Venus yet again. The colors represent temperature. Yes. Yeah, that's the color bar here at the bottom. Very sus indeed. So let's read about finding the suspects. With these simulations, the authors observe some key trends. They find that all collisions involving a low mass, 0.01 Earth mass impactor lead to mergers, but for collisions involving a high mass impactor, the outcome depends on both the impact parameter and velocity. High mass impactors with a low impact parameter result in mergers regardless of initial velocity. However, for high mass objects with high impact parameters, collisions that are not head-on but at an angle, so that kind of just like swipes by, they find that the impact velocity determines the type of collision, with velocities of 10 kilometers per second resulting in graze and merge collisions and higher velocities of 15 kilometers per second leading to hit and run events. Each of these scenarios leads to different transfers of angular momentum, resulting in very different post-impact rotation rates. So the purpose of this study, it seems, was to understand what is the outcome of these collisions. Does the smaller body collide back in, or does it kind of fly away? So that's why they suggested like the hit and run, grazer, and merger outcomes. To match Venus's present-day rotation, the impact scenario must leave the planet spinning with the post-impact rotation rate exceeding 48 hours. Oh my god! Oh, thank you, Shemi09EU, for the 5 gift memberships on YouTube. And congratulations to, Michael Saab Aussie, Kai Zulbergsky, Subasa Bart, and King of Nebushes for receiving gift memberships. Thank you so much to Shami. Thank you so much. Oh yeah, no, my notifications are going off. Wow, I really appreciate that. And congratulations to everyone who got memberships. Wow, I'm at a loss of words. Sorry, I'm a lurker. Not sure how to jump in chat. Well, thank you so much for your support. I really appreciate it. The memberships are great. I guess I can give a brief spiel about what the memberships do. So, for me, I kind of set up the membership system as like a way to support me. But you can still access like the same content. The other bonus is that you can join into the Discord, and then you get access to a members only channel, which we've been doing some voice calls. And then if you're on a red supergiant tier, which if I recall correctly is the tier you get when you're giving gift memberships, you also get access to my weekly Z-mail, which kind of highlights some of my more IRL updates and some updates of my life and research. All right, so let's keep reading. All right. So now they're comparing to Venus itself. To match Venus's present-day rotation, the impact scenario must leave the planet spinning with a post-impact rotation rate exceeding 48 hours. The transfer of angular momentum during the collision, as well as the initial rotation of Venus, will determine which impact scenario is consistent with the rotation we measure today. The authors find that 17 of the 19 collisions result in a post-impact rotation in agreement with this constraint. Out of those, they find that 2 collision scenarios lead to the slightly retrograde motion similar to that of Venus today. To further analyze the list of suspects, the authors examined the debris disk generated by each collision. Since Venus does not have a moon, scenarios producing massive debris disks are disfavored because such disks may contain enough material to coalesce into orbiting satellites, and Venus doesn't have a moon, so that makes sense. They discover a positive correlation between disk mass and post-impact angular momentum, and find that the collisions that are compatible with Venus's present rotation also tend to produce lower disk masses. This paints a consistent picture with Venus's lack of a moon. While these scenarios leave the authors with many combinations of initial conditions that create post-collision rotation speeds and debris disk masses consistent with Venus's present-day properties, the author suggests studying the effect of post-impact temperature on Venus's thermal evolution as an additional avenue for differentiating between these impact scenarios. I think that is very important because I think Venus's thermal evolution is a very interesting aspect of sort of how it became so different from Earth. They find that their collision models produce diverse thermal structures and melting profiles of Venus, and they plan to further study these in their future work. This study demonstrates that a high-speed collision could explain Venus's slow retrograde rotation and lack of a moon. That is really interesting. So a planetary hit and run, literally. However, because the suspect fled the scene billions of years ago, we must work backwards to narrow down what occurred. Future work examining these post-impact temperatures profiles may help determine more likely collision scenarios and reveal how a planet similar to Earth became an uninhabitable and formidable world. Understanding how Venus became so radically different from Earth is crucial for explaining the diversity of terrestrial planets beyond our solar system and may hold keys to understanding planetary habitability. Yeah, so yeah, they took into account all these different things later in the paper. So thank you, Tori Bonady, 5th-year PhD candidate studying exoplanet atmospheres at the University of Pittsburgh. Thank you for writing this amazing article. This was super cool. Yeah, I guess I didn't know that. So the reason why Venus has no moon and spins retrograde, or the opposite way around, is because it could be due to a literal planetary hit and run. What if it was multiple impacts? Well, the solar system at its start was a very active system. Like the Earth was getting bombarded by all of these little planetesimals and small rocks. There's a specific name for this. Active area solar system. Let me see if I can try to pull up the Wikipedia article. Formation. Okay. Oh shoot. There's a specific name for this very hectic era. Oh, it's called the heavy bombardment. Yes. Yes. Maybe I'll screen share this real quick. So the late heavy bombardment, then there was also just a normal heavy bombardment, if I recall correctly. Yeah, very, very crazy era. Oh, this was after the moon formed. Well, what I'm trying to get across is that the early solar system was a very, very active period. I don't think this is the one I was looking for. Wonder what assumptions went into their model of Venus's pre-impact mass and angular momentum. That's what I'm wondering as well. Let's see. I'll quickly look this up and then we'll go into the... Maybe there was no name for the period of incredible impacts that first occurred at the planetary formation era. Yeah, I guess late heavy bombardment. Late heavy bombardment, gravitational disruption from the outer planet's migration sent large numbers of asteroids into the inner solar system. But yeah, I guess what I'm trying to get across is that the early solar system was a very active period of time. And so it's likely that, you know, there could have been multiple colliders. non-rotating Venus. Yeah, so they had 81 different simulations, some of which included a non-rotating Venus. I'm gonna open this article and see. If you go to the Astrobites link that I've pinned, you can go into the top here and then click the research article there. Sometimes it's not open access. This one might be. I'm not screen sharing because sometimes my like institution name comes up. Pre-impact temperature profiles. Okay, so they say that both models assume a differentiated planet with an iron core 30% and rocky mantle 70%. And so they had a temperature profile in the two different layers. Oh, so they had different spin periods. 0, 2.5, 6, 12, and 24 hours. Oh, they have a section on initial conditions. Yeah, they talk about like the angle of which the impact occurs. Yeah, they have a lot more details in the paper itself. I don't know about the copyright regulations, so I'm also not screen sharing this, but if you are curious, I definitely would recommend looking at the initial conditions section of this paper. Yeah, I guess they didn't really care as much about, you know, getting like the interior structure right. That's also very hard to build correct initial conditions for because we have very little information about what the inside of Venus looked like at the early universe, not the early universe, the early solar system. But what they were trying to see, the point of their 81 simulations was try to piece together what would happen if a collider grazed by Venus, if it merged with Venus, or if it kind of like rebounded off of Venus, and see what would happen to Venus's rotation rate, and the formation of a moon. There's a joke that the Kepler Space Telescope failed to find proper Earth analogs, but found tons of proper Venus analogs. I'm not quite sure what you mean by that. I think, Kepler Space Telescope did find a lot of, rocky planets, but the way that the Kepler Space Telescope works is that it relies on transit detections. What that means is that when a planet crosses in front of its star, it causes a temporary dip in brightness. And so when detecting rocky bodies, they are very small. And so it's very hard to find small rocky bodies that cross in front of a star. And so the rocky bodies that we've been able to find is when the star is smaller. And so when the rocky body passes in front of it, the dip in brightness is sort of like a larger percentage compared to the original brightness of the star. But the issue is, in those systems, like, for instance, like red dwarf systems, where the star is very small and red, those stars also tend to emit a lot of dangerous radiation. And we also have a higher chance of detecting it if the planet is closer. Oh, thank you, Murphy Moo. If the planet is closer to the star itself. And so you get a lot of systems detected by these transit telescopes where the planet is very close to the star. It might be roughly the same size as Earth or a rocky planet, but it's very close to a star with a lot of radiation. And so what happens is that unfortunately these planets are not likely to be habitable because they're experiencing so much radiation that they would basically fry away. If I recall correctly, in some instances, the radiation is so powerful that it can also lead to the atmosphere literally being shedded away. And so that's just an unfortunate consequence of how we detect these planets, which is why we're getting new telescopes that are using more different methods of detecting planets, such as one where if a planet is orbiting a star, there's sort of a push and pull that happens gravitationally, and so you can kind of measure these small changes in orbit. There are some telescopes that are trying to directly observe, like literally directly image these exoplanets. There are some that are trying to use microlensing or like microgravitational lensing in order to detect exoplanets, and that will give us a bigger diversity of planets that hopefully could be habitable, or at least give us some more insights into the diversity of exoplanets that are out there. You, sir, earned a follow instantly because is your torso the microwave radiation from the beginning of the universe? Yes, it is. I am canonically a photon from the first light of the universe, the cosmic microwave background. But today we are talking about exoplanets. A very, very different topic, but I do astrophysics content, yes. Hi Z, hope you're doing well. Hello Bada Sheep, thank you for the astromagical content on YouTube. Well, thank you so much for finding me. Truly making my For You page much better. Yeah, I'm actually curious about where you guys have been finding my channel. I think there's been a recent uptick of people who have found me through my video with Phi, which was on giant bacteria, giant viruses, where I made a little bit of a cameo because it turns out that the reason why we can't resolve giant viruses with a normal microscope is a very similar reason as to why we struggled to resolve the furthest galaxies in the universe. So basically same problem, but very different scales. And so a lot of people found me through that way. This has made my Twitch much better. Thank you so much. I think quite a few people found me on Reddit as well. I found you live on my subscription page. Oh, I see. Thank you, Unit. Yeah, I think a lot of people have found me through the V-Theorem group, so let me plug them real quick. V-Theorem is actually a group of VTubers that I'm part of that focuses on educational content, so I highly recommend you check all of them out. They are amazing. Oh, I guess... Oh, it's kind of glitching out on the Twitch side because Syzygy is also linked on there too. I discovered Z through Phi's video. Yeah, a lot of people found me through that video actually. But yes, great. In the meantime, let me try to pull up this next article. So we have one last JEDI and Exoplanet for me. Yeah, I see the link to Syzygy, but that's it. Yeah, it's not popping. Oh, yeah, it just popped up on the Twitch. Oh wait, no, that was just Pembu. Thank you. Yeah. You know what? I'm gonna check that. It must be different between Twitch and YouTube. I found you through a green alien doctor. Yes, Faye is amazing. Oh my god. Faye is amazing. Isn't Syzygy doing hags in STEM? Is she? Let me see. Let me pull up my Twitch. No, I don't think she's streaming right now. But I was on the very first Hags in STEM when it came out. That was I think that was our first collaboration. It was great. But we are going to be collaborating more often. The issue is that across all of V-Theorem, the time zones are the most challenging between Syzygy and I. But we've been making it work, and there have been some instances where we've collabed together. Soon, not yet, 1.25 hours from now. Oh, I don't know if I'll be streaming by then, but definitely go check her out. But yeah, no, Faye was also one of the first VTubers that I met. When I was first getting started, I was kind of nervous because I didn't think that there would be a lot of VTubers in the educational space, and boy was I wrong, because there are so many, not just VTubers, but also streamers that focus on making educational content accessible. And I remember I messaged Faye, I think like a little bit prior to my debut, just like introducing myself and asking some questions, and she's such a sweet person. And then we've collabed a few times. We did collab for Valentine's Day, we did a collab for Halloween, that was a lot of fun, where we made like pumpkins. And yeah, it was great. I thought the challenge would be your areas of expertise. Oh, you mean like coming from astrophysics? Well, Faye and I are both very science-oriented folk. Will you not be on this Hags and STEM? No, I will not. Though maybe I should message Syzygy to run that back. I am collaborating with NEP in a few weeks, if I recall correctly. I think we're doing something for Valentine's Day, actually. Oh, yeah. But definitely go check it out. Yeah, nerds. Yeah, we are such nerds. But we're proud of being nerds. And we're also very proud of our nerd communities that we've grown. The Specie members and the Orbies. You guys are great. Alright, so we're gonna read, this is our last Exoplanet article, and then if we have a bit of time, I might quickly show you this Z Machine article that I came across as well. Astrophysics with psychology, I can't make it work. Actually, no, there's a lot of interesting stuff. We were talking about, like, you know, loneliness in space, how to deal with, you know, a group of people being in a confined space for long periods of time. There's a lot of research at the intersection of, like, astronaut behavior and psychology. Because if we are to ever become a spacefaring civilization, it will take us years to go to Mars. And there's also a big time... If you thought the time zone difference between me and Syzygy was bad, think about the time zone difference to go to Mars. There's also going to be like a slight... if you go far enough, there's also slight time delay, so live video calls aren't even an option either. And so these are all very big considerations to think about, especially when we're sending humans into space, because it's not only important to think about their physical health, but also their psychological health as well, especially if we want to create sustainable civilizations. Yes, I've heard about the psychological effects of journeying to Mars and how to lessen them. Yeah, one of the things I think we talked about briefly was also like romance in space and how to deal with that. Or like how being in a confined space could... Whoa! Whoa! Wait, I'm so sorry, Orbeez. Okay, there was a bird that like flew like straight towards... I have like a window here. There was a bird that flew like... Whoa! There was like a giant hawk that like was like... Okay, I have no idea what bird that is, but there was some like hawk-like bird that just like flew straight into the window, and like right before it hit the window, it like flew up, and then the bird like flew down again, like basically like jet dived. Okay, that was crazy. Wow, birb. That was insane. 1 minute light speed delay between Earth and Mars. I thought it was longer than that. Light delay between Earth and Mars. Yeah, light takes about 3 to 22 minutes to travel from Mars to Earth. Yeah, so there's no way to do video calls. Yeah, nature is wild. See, he's wearing the bird seed perfume again. I've never seen anything like that. I am like at a loss for words. Collab with the ornithologist VTuber. Oh, I wish! If there's an ornithologist VTuber, that would be amazing. The bird wanted to learn too, yeah. What's there to say that a bird can't go to space? Actually, I'm curious. This is a question I ask a lot of people when I meet them for the first time. If you were doing what you were doing, what would you... What career would you have wanted to do? I phrased that really poorly. Like, for instance, if I wasn't doing astrophysics research, when I was younger, I actually really wanted to be an ornithologist. Like, I wanted to study birds. I still do, like, a little bit of bird watching here and there. Hawk wants to join the stream. Ornithologist collab right now. The hawk needs to come back. I'll open the window and then we'll have a collab. It would be very, very scary. To astronaut, but I realized I was gonna be homesick. Actually, oddly enough, I have never wanted to be an astronaut, which is really, really interesting. Because typically that's what, you know, people go from astronaut to astrophysics. Like, that pipeline is very set. But I also feel like I could not be away from friends and family for that long. Plus, I don't think I'm built to be an astronaut. Like, for instance, like, do you see my health right now? Like, I have so much congestion in my nose just from coming back from, like, 5 days of, like, travel. And now... let alone being in space for months, I don't think I can make it out. If I wouldn't go to STEM, I would be a historian. Oh, that's a good one, too. A historian would be really interesting. Wait, I have the funniest story. I met someone a few days ago who is a historian, and was doing like research on this like huge like flood. There was this giant flood that stretched from like Seattle to Los Angeles back in like the 1800s. And basically, like, his research is, like, all on this, like, giant flood that happened in this one particular year. And there's, like, so much detail about it. There's so many angles as to which you can explore this flood. Whether it's from, like, a historical angle, but also from, like, a political angle. Like, how did the lawmakers deal with the aftermath of this flood, or how did they regulate the infrastructure? You can also think of it from like an architecture perspective. Apparently, like, some people built like their houses on stilts back then. There's also like an environmental perspective. There are so many different ways to think about like this one event that I have like previously not heard of. And I just found that really, really fascinating. Like, there are so many crazy ways to go deep into something that you really enjoy. Isn't that what happened to the Kelly twins? Oh yeah, one of them is like a few minutes older. Yeah, I mean, if you're traveling within the solar system at a relatively well, we're not at like speed of light travel, then being like coming back and like Earth being like 50 years older than you is not going to happen. But yeah, it's definitely an interesting effect of relativity. I wanted to be an engineer working on projects like SLS, but I couldn't get a grasp on all the maths. Yeah, it definitely is a lot of math, though. One of the things that I'm hoping to do with this channel is I've heard a lot of stories from you Orbeez actually about, you know, wanting to go into astrophysics or finding challenges with learning math or physics or getting started. And it is true that there is definitely a learning curve. But that being said, that's why platforms like Astrobites exist. They take articles into sort of bite-sized pieces and sort of getting you familiar with the language. You know, when you're learning a language for the first time, like, one of the best ways is to just immerse yourself as much as possible. That's why, you know, when you're learning a language for the first time and you visit the country, where everyone's speaking it all the time, even if you are relatively a beginner, like, the amount that you learn is so quick because you're just immersing yourself. And so, like, Astrobites may not be directly reading from the research paper itself, but in some ways, I kind of consider it like immersing yourself from a good starting point as well. I am an engineering student. Hello, hello. Whoa, hello, what the dog doing? Thank you so much for following. Video editor, ooh, yeah. History and astrophysics Miyake events. What are Miyake events? That sounds familiar. Oh, okay, yes, I did hear about this. It's like basically these like, yeah, it has to do with the trees, but basically you can, by looking at trees, you can sort of trace these cosmic radiation events. Yeah, no, this is some super cool stuff. Did you mention the Z machine? That's in an article that we'll take a look at a second. We have one more article to go through really quickly. He looked really tired, yeah. Alright, so let's get started with this article, and then we will end up with the Z machine, and yeah, I think that will be a pretty solid stream. So this article also has a very funny title. Use the polycyclic aromatic hydrocarbons, Luke, the JEDI's view of a protoplanetary disk. The flying saucer edge on disks near infrared silhouette revealed by the JEDI's program. That is so cool. See, astrophysicists are great at naming things. Forming planets is pretty complicated, and a lot of models rely on several underlying assumptions about the physical structure of the host protoplanetary disk. How is their dust and gas distributed? What is their radius? What is their vertical structure? Getting a grip on vertical structure is super important. It tells us how the dust in the disk is distributed by the turbulent motion of the gas, which is important in understanding disk evolution. Dust grains that are not stirred very high are said to be settled. These are typically larger grains greater than 10 microns in size. This is because the smaller dust grains follow the turbulent motion of the gas more, but larger grains don't. Think about kicking up tiny sand grains versus larger pebbles underwater. The authors of today's article have used data from the NIRSPEC instrument on the James Webb Space Telescope as part of the JEDI's program. The authors studied the protoplanetary disk known as the flying saucer. Oh, this is so cool. And extracted information about the vertical structure of the dust. The flying saucer is especially interesting because it is backlit by an ambient emission region with polycyclic aromatic hydrocarbons, or PAHs. These PAHs are excited by ultraviolet photons and then emit infrared photons, which are later absorbed by the disk at specific wavelengths. As a result, the midplane of the disk, where most of the mass is and where planets are forming, are silhouetted in contrast to the upper layers. Okay, so let's take a look. Okay. Oh, another beautiful diagram. Oh my god, I need to know how they made this. This is so great. The congestion thing is probably allergies or sinus. No, I actually got sick. Like I had a sore throat a few days ago, and then I was coughing. So I'm at sort of the tail end of the sickness. Let's see. Illustration of the PAHs emitting infrared rays from the ambient emitters. So PAHs are these little molecules here. So these polycyclic aromatic hydrocarbons absorb UV, okay, and emit infrared photons. The protoplanetary disk, so this is like the precursor to the solar system. Midplane absorbs the radiation. The interstellar dust causes extinction. And then James Webb observes the infrared rays. Yes, so these infrared photons then cause this reddening, and then that is what the James Webb Space Telescope observes. Wow, this is a great figure. Galaxy brains, thank you. Hi, Warpy! Thank you for swinging by. Sorry, I'm having a bit of water. Oh, what? What's going on here? Oh, this image must have not loaded. Give me 1 second. Oh. Oh no, there must be like a glitch. I think there must be an image here, but it's not showing. Let me see if I can just pull it up. If it's in the Astrobites article, I assume it's okay to share it. Let me see if I can. Oh, this article is a little bit broken. But okay, there's an image down here, so we'll get to that. Let's read on. To study the disk, the authors created a model using the radiative transfer model RADMC3D, which simulates the path that the light emitted from the disk. So the light from here goes into James Webb. So it simulates that light. They included the ambient emitting region, light from the star scattered off in the disk, and a foreground cloud of dust to account for interstellar dust extinction. They then combined the model with the point spread function, so the limited telescope resolution of James Webb. Yes, how the light from a point spread spreads out due to the complex honeycomb-like mirror shape, and compared this to observations, which can be seen in figure 3. Yes. So the authors found that the models matched the observations well, and they could then infer properties about the disk's vertical structure. From both their models and observations, they found a few key results. Okay, so let's take a look. So here they have the synthetic models convolved with the JWST point spread function. So basically they simulated the object, and then they also simulated the telescope's instrumental effects in the top row. And then these are the actual observations. I mean, visually they look quite similar. The emitting background dominates the emission at 3.29 microns, which represents the PAH molecules. And H2 emission dominates at 3 microns. The authors argue that the models and observations look similar to each other, allowing them to infer properties about the disk. I mean, it looks pretty similar to me. Flying saucer, you are shorter than I expected. First, the disk has a radius of 235 AU when looking at the small grains, which disagrees with the radius inferred from the millimeter observations using ALMA. Previous results found a radius of 190 AU. So an AU is the distance between the Earth and the Sun. But the authors highlight that the ALMA data traces larger millimeter-sized grains, whereas the JWST data traces the micron-sized dust. So ALMA is a radio telescope. It's like an array. And so they're comparing the observations from James Webb and ALMA because they sort of probe different regions of this object, or different grains in this case. The cause of this radius difference between dust sizes remains unclear. A Star Wars quote. Oh, this one here. Oh, that makes sense. Second, the authors discovered that the smaller grains are less settled than the larger millimeter-sized grains. That makes sense. This matches well with expectation theory, and the authors plan to conduct a follow-up study to fully analyze the disk structure and properties. Finally, they found that the vertical extent of the small icy grains is larger than expected. By balancing forces due to the disk's gravity and gas pressure, we would expect the grains to reach a certain height above the midplane. The models suggest, however, that there ought to be a small fraction of ice-covered dust that is even higher up. The authors caution, however, that the model parameters can be degenerate, which means that multiple parameters give the same result, making it hard to distinguish which individual parameter is responsible for the results in real life. So they found a lot of different aspects about the grains and the height of this planet-forming disk. The flying saucer provides a unique opportunity to study protoplanetary disks using the polycyclic aromatic hydrocarbon emission behind it. Keep an eye out for the author's follow-up study. Great. Thank you, Joe Williams, a third-year PhD student at the University of Exeter in the UK, for writing this great article. I love the Star Wars references. Woohoo! Wow, we covered 3 articles. We are zooming. Typically, it takes quite a bit of time to go through 3 articles, so. Oh, I'm sorry. I realized that the article on the Z machine is not about the Z machine, it's about the Z facility. So, that's all for the exoplanet related articles, but I did want to say that we're going to quickly skim over this Z facility article as our final huzzah. Oop. Let me unpin this. Come on. What? It's not letting me pin this on Twitch. Come on. It's not letting me pin it, but I will, for the Twitch folk, it's linked there. 2 of them were really sus. Yeah, no, that was really funny. I guess the title of this stream was very appropriate. So we're gonna quickly skim this article because it has a reference to the Z facility. This is not on exoplanets, but I thought it'd be fun to share to wrap things up. Alright. A student once asked me, how can we measure the temperature of the sun if it's so hot? Wouldn't our thermometer melt? They were onto something bigger that is fundamental to astrophysics in general. The truth is we rarely physically measure anything we study. The thermometer would melt. Yeah, and most things are too far away to set a thermometer anyway. Instead, we must infer measurements from our observations using physics models. For measurements of the sun, we use the standard solar model. This is the framework you'll learn in any introductory astronomy class. The sun is a giant sphere of gas with a core of hydrogen undergoing nuclear fusion and releasing energy. That energy is transported outward via radiation, then convection, and eventually reaches the surface, causing the sun to shine. See a schematic of this model in figure 1. Combining this model with observations like luminosity or brightness and surface abundances from spectroscopy allow us to infer properties like temperature, density, and interior structure. Wow, this article is really persuading me to do that stream on, I was going to do a live lecture on spectra distribution fitting, which is basically using these methods, but for galaxies. Another way the sun's interior structure is probed is through helioseismology. Oh, this is so sick. Or observing oscillations on the sun's surface. It works just like seismology on Earth. Oscillations measured on the surface allow us to understand how waves propagate from below and what the structure down there must be like. That's exactly what they did to understand the layers of the Earth. This is particularly useful for directly measuring the depths of the sun's convection zone without relying on models. The solar problem. A little over 2 decades ago, tension began to rise between observational methods. Specifically, feeding new solar abundance observations into solar models predicted a shallower convection zone than what was measured from helioseismological observations. So are our models wrong, and how can we test that? Today's authors tackle these questions by creating sunlight conditions at Sandia National Laboratory's Z facility, so that they can compare the models to actual measurements. This is great. Wait, let me see if I can pull up the link. Oh wait, this does link to the Z machine. Wait, this is great. Oh my god, we're gonna look at this. Z Pulse Power Facility. Sandia's Z machine is the world's most powerful and efficient laboratory radiation source. Yes, this is the Z machine. Okay, wait, I guess I didn't skim it right the first time. Hello, what the dog doing? Thank you so much for first time chat. There was a planet that has molten diamond as rains. Is that thing still relevant? We discovered something cool. It can provide significant information. Yeah, I mean, we find planets that are like raining all sorts of different things. Or even moons. Shoot, what was the... I'm gonna look this up real quick. There was the... Oh my god, it's on the tip of my tongue. Yeah, Jupiter rains diamonds. Yeah, Titan, Saturn's moons, has a methane-based rain cycle. But if you're talking about exoplanets, this is really interesting in particular because it kind of shows like how far our technology has been able to go, such that we can just look at the light of an incredibly distant exoplanet, and from there be able to decipher what its rain looks like, or what its atmosphere looks like. And so, you know, maybe raining diamonds may not be suitable for life, but we also only have one example of what life looks like, Earth. There might be planets that are based off of like silicon-based life, or, you know, Europa, which is a moon in Jupiter, which isn't even a planet, that has an ocean underneath its surface that might host water-based life. We don't know what life out there looks like, so who knows? Diamonds in a cosmic scale aren't all that rare, no. Well, for something like Jupiter, it occurs because, if I recall correctly, it has like carbon in its atmosphere, and because the pressure is so high, it collapses into diamonds. By Oshi reading about my favorite toy, the Z machine? The Z machine? Thanks for the clarification. Yeah, no problem. This is great. It uses high magnetic fields associated with high electrical currents to produce high temperatures, high pressure, and powerful X-rays for research and high energy density. Wow, they use the word high like 6 times in that sentence. The Z machine creates conditions found nowhere else on Earth, located in Albuquerque, New Mexico. Z is part of Sandia's Pulse Power program, which began in the 1960s. Sandia National Lab. Please, please. Z. This gets even better. Z researchers. Oh my god. Please. Okay, if there is an Orbeez who is part of this group, like, please do let me know. Please. Z researchers meet the toughest scientific challenges with innovation and ingenuity that breed groundbreaking results. Read Z's publication. I love how they just call it Z for short. And the sections below to learn more about this work. Z provides, what can I say? Z provides the fastest, most accurate, and cheapest method to determine how materials will react under high pressures and temperatures. Characteristics that can then be expressed in formulas called equations of state. Of course, I provide the most accurate and cheapest method. This article is written by someone who knew how to make a joke. Yes. Z facility and Z collab, please, please. The Z machine, Z research, the Z machine. Oh my god. Z is crucial for national security. Wow, this is great. Oh, look at these gorgeous images. This is so peak. I'll have this linked. I mean, if you just look up Z facility at Sandia National Lab, you'll find it. But I'll link it in the YouTube description as well. Actually, recently, the 30-meter telescope, like, shouted me out on their X platform. Maybe Sandia Labs could shout me out, too. This is a dream. This is crazy. Here, let me go back to the original tab. So let's see how they use the Z facility. So this is the standard solar model showing the interior of the sun. The opacity used in the model determines the sizes of the radiation and convection zones. Something researchers suspect the solar models could get wrong is opacity, which describes how often photons get absorbed as they try to push through plasma to the sun's surface. Because photon transport is so important in the sun, opacity has a big effect on the interior structure models predict. Essentially, if the solar opacity in models is higher, they would predict an interior structure more like that measured from helioseismology. And it could currently be wrong. The opacity used in models is an approximation because we don't fully understand opacity in plasmas as hot and dense as those in the sun. To better understand opacity in sun-like plasma, today's author created an extremely hot and dense oxygen plasma in a lab. They focus on oxygen because it is one of the elements that affects opacity the most at solar temperatures. Oh, thank you, Jason, for subscribing. Recreating solar conditions is quite difficult, so the plasma wasn't as hot and dense as the sun, which, with a temperature and density lower by a factor of 10 and 1.3 respectively. Still, this was the hottest and densest oxygen plasma opacity measurements have ever been taken from. Then they measured the radiation that could be transmitted through the plasma using a handful of spectrometers to limit experimental uncertainties. Finally, they compared these opacity measurements to 7 state-of-the-art opacity models commonly used to model the sun. Okay, so this is a figure. Opacity, okay, on the y-axis as a function of wavelength for a few of oxygen's key atomic features. Black points and error bars show the measurements, and the colored lines show predictions from their different models. Okay, cool. This is great. Let's read on. As shown in figure 2, the opacity measurements match the models surprisingly well. I think there's a few differences, but let's see. Like, I think there's a difference here, and I'm wondering, it looks like this spike is not in black. But let's see. The slight differences, this is the first time such a plasma has been studied in a lab. The slight differences between the measurements and models will be used to make model improvements, but these differences aren't great enough to solve the solar problem. The oxygen opacity isn't high enough to make models match helioseismology measurements. Other possible solutions do exist though. For example, a similar study done with an iron plasma did result in higher opacities, which partially resolves this problem. As our laboratory technologies improve, we will be able to make even hotter and denser plasmas to replicate the sun better. This will ultimately improve the standard solar model, and therefore our understanding of all other stars in the universe without any melted thermometers. Well, this was a quick and easy read. So I guess they're going to be using the Z facility even more in order to model these plasmas. Thank you, Anelia Anderson, for this insightful article. I still just like cannot get over how cool this is. Wait, I'm gonna see if they have a... Oh, they do have a YouTube. Oh, it's not letting me click their like X account though. Let me see if they do. Oh, they have one for Sandia Labs. Wait, let's see if I search Z facility on X. Sandia Z facility. Oh, they only have their Sandia National Labs. That makes sense. Super cool though. Super, super, super cool. When the Z researchers at the Z facility write a Z article about their Z findings. Yeah, no, this is super sick. Alright, well those are all the articles that I wanted to cover. This was super, super great. Let's see who's streaming. Let's see. Kim is streaming. E to the iPie I rated last time. Oh, Tofu's streaming. I haven't visited Tofu in a while. Alright, Orbeez, we gotta vote. Who shall we raid today? Oh, let me refresh just in case, because sometimes the... Look at you remembering to raid. High five. I'm so bad at this. Well, it's because of... Whoa. Oh my god. My voice is going away. It's because I have Twitch open, so... I guess no one's doing educational content except E to the iPie. Tofu's lovely. Alright, should we raid Tofu? Alright, so... For those of you who aren't on Twitch, please hop on there. Z dies live. No, I won't die. I will drink a warm glass of tea. But, really quick, once again, another reminder, I am streaming tomorrow. Hopefully my voice will be a little bit better. We are doing a nerdy book showcase between Stella and I, who is a new astronomy VTuber. I think we'll be doing dual streaming, so check that out. I will have the YouTube link set up soon. So, yes. I will see you guys tomorrow. 2 Z streams in 1 weekend. Let me do raid, tiny toxic. Tofu, do you use related literature that are less than 10 years old? Yes. I mean, typically that's a lot of research. I'm not sure if I understand your question, but feel free to join the Discord and ask me there. Yes, speeding at C, rating at Z. Wait, I think that would be great. Hold up. Rating at Z, at C. It's a Z raid. Okay, so this will be our message. So if you are on YouTube, please join the Twitch. Thank you all so much for joining once again. I hope you guys have a spectacular day, and I will see you in about less than 24 hours. See you guys very soon. Bye-bye. 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 Bye-bye.